knew it was coming. If we live in Austin, we will have a cowboy hat. We're doing circular motion this time. That's sigma f equals mv squared over r. And so we're going with the cowboy using his lasso. Alright then, here we go. So we start this one out with a sigma f formula again. This time it's mv squared over r. And that shows up on our formula sheet as f sub c equals mv squared over r, and that can confuse us because we can want to put that onto our free body diagram. But just like for the other two, this does never go on a free body diagram. This is what all the forces on the free body diagram have to sum up to equal. And we started just the way we do all the other ones. We do a free body diagram, we figure out what the forces are. The good news is that because it's a more complicated situation with circular, we hardly ever have really complicated sigma f's, and the problems end up being a little easier. Let's do a quick example of some of the forces equals mv squared over r. And we're going to do it for a car going around a circular track. So here's my car over here. It's going to be going around that way, all the way around the track. And the one thing that's really important to know about circular motion is that the direction of the force has to be towards the middle. I can call it sigma f. All the forces added together have to go towards the center because that's the way that I'm changing the velocity. If this is my velocity there and I want to keep going around this corner, my force has to continually be pushing me towards the center of the circle. And so all of my forces have to sum up to get to the middle. And so it's actually better on this one if I look at it from the side and do my free body diagram. So here's my car over here. I know that one force on my car, oh, I like different colors. Let's do different colors. One force on my car is the force of gravity. And it's going down, I know. And then because it's on a surface, because I'm on a track, I'm going to have a force going upwards. Force, normal. And they have to give me a mu in this because if I have just those two forces, I'm never going to be able to go around a circle because I have nothing going towards the center of the circle. So in this, they have to tell me a mu, and so therefore I'm going to get a force of friction going towards the middle. And it turns out that since normal force is going to cancel out gravity, frictional force is going to be all of my forces. And so in this case, sigma f equals mv squared over r is going to be frictional force equals mv squared over r. Notice it's just one force. That's mostly what we get for circular. We only get one force because if it gets too complicated with circular, we can't redo the problem, so it's nice for us. If we remember, the formula for frictional force equals mu f of n. And f of n in this case is going to be mg because it's the same thing as gravity over here. So that means that I get mu mg equals mv squared over r. Oh, that's not very good. And my m's cancel. And so it turns out that it doesn't really matter what mass of a car goes around. If I have the right coefficient of friction, it's going to make it around the circle. Just a quick example of a friction one. We'll have more in the future. Okay, so let's write down some of the formulas, make sure you know them. The centripetal force is mv squared over r, and that's what it's going to say in your formula sheet. And you have to realize that that is not a force, that is a sigma force. And I like to call it a necessary force, because what that means is that if you don't have all the forces equal mv over squared, it won't, v squared over r, it won't go in a circle, it'll go straight, or it'll slip, or you'll, if you're trying to go around a corner in a car, you'll hit a tree if the mu isn't big enough. And so that's that. And then also, there's a separate one for just acceleration. So occasionally they'll ask you for the centripetal acceleration of the centripetal force. We know that F equals ma, and so the reason how we get this is we just take the m out, and that gives us v squared over r. My direction is always towards the center. If my force isn't going towards the center, so I'm going to go in a circle. And realize that both the velocity and the displacement are not towards the center. Both of those are along a tangent. So if you look at this picture down here, we have an acceleration radial, which is another way of saying centripetal. And if I'm speeding up along my curve, I also have an acceleration tangential. And so if I'm speeding up around a curve, my total is actually going to be towards the center and along it, and so I get an a total there. So occasionally they make you calculate that total acceleration, if they're saying that it goes faster around the corner. So there actually are two accelerations when we're talking about going in a circle. This one here makes it go in a circle. This one here makes it go faster around the circle. So realize there's two in there, and sometimes you have to add them together with a squared plus b squared equals c squared. One set of circular motion that's so common that they have a special situation for it, I want to talk about a lot, is vertical loops. So what a vertical loop is when my circle is not flat like when I'm in a car, but when it's going straight up and down. And there's two ways we do that, mainly with tension or with normal force. Tension would be like if, in this first one right here, if we say that's a yo-yo, and I'm doing it around the world in yo-yo, and so my velocity is going around this corner, around that corner. I don't normally write velocities on there, but otherwise it's hard to figure out what's going on in the problem. Since I'm doing something else, I'm also going to change my color. On every force problem that I do, I have to find all the forces on it. And this one I'm finding in three different places. At the top, up here, the bottom, down the sides. At the top, I know that there's one force, that would be gravity, F-G. And it's going straight down. Didn't do a very good G there. Anyway, I know that's going straight down. And since my rope is going down at that point too, my other force, which is force tension, is also going down. Since they're both going down there, I know that that's my sum of the forces, and that's all I have. So I basically say that force tension plus force of gravity equals mv squared over r at that point. I can't ever make a very good G. Down at the bottom, my gravity is still going down. Let's try to make a better G this time. A little better. And then my tension also goes up because tension can only pull. So my Ft is going the other way. And so they're going in opposite directions this time. And I know that my force tension has to be bigger because some of all my force has to be towards the center of my circle. And so that means that it's force tension minus force of gravity equals mv squared over r. So a lot of times in these problems, what they will do is they will say it goes at a constant speed all the way around, and they'll ask you which one has a higher tension. And you can look at this pretty easily and see, look, if I take the top one, I'd subtract g to the other side. That makes it smaller than mv squared over r. Do the bottom one, I take gravity, put it to the other side. It's greater than mv squared over r, so my tension always has to be bigger at the bottom of a vertical circle. The other odd point is at the side, because at the side, my gravity, last chance for a g, oh, better maybe, goes that way, and my tension goes that way. And since my centripetal force has to go towards the center, my gravity cannot add to that because it's going straight down. So in this one, it's just force tension equals mv squared over r. Wow, that's really kind of hard to read. Here, let's look at a better version. Through the magic of video, you can all of a sudden read my handwriting. And I put all the forces on there. I put the velocities on a lot of those to show which way it's going around. But usually you don't put those on free body diagrams, so that's kind of an anomaly there. But you can see the equations and how it changes. And so they'll give you problems where you have to use which equation it is for the top, the bottom, or the side. Occasionally, very occasionally, you'll get one on a strange place, like at an angle. Like they'll say that angle is 30, and then in that one, you know, tension goes towards the center, and you have to split gravity into components. That angle is the same as that one. So this side right here, let's do a different color because I like to see different colors. This side right there would be mg sine theta. And for that sideways one, it would be ft, and be minus because it's going away from minus mg sine theta equals mv squared over r. That's kind of an odd one. They don't do that very often. Mostly it's just these main ones here. But you could do one at an angle, so realize that could be coming. Also notice that over here, which is my roller coaster one, it's the exact same equations. The only difference is it's normal force providing me with the force towards the center every time. Gravity either helps at the top or is against it at the middle, at the bottom, or in the middle, doesn't affect it at all. So it's the same three equations, it's just using normal force instead of tension. That makes it kind of nice because we don't have to have a whole other set. Yum! 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 So it's peanut M&M's this time. Cowboys and chocolate goes together, right? I guess. Don't really care. We like M&M's. The next kind of situation circuit that we're going to talk about is any kind of satellite going around the Earth. So if we put the Earth in the middle, oh, I'm not writing. Earth in the middle, something going around the Earth. The main one we talk about is the moon, right? Because that's the biggest satellite we have. They all work the same though, so it's nice. In this case, sigma f equals mv squared over r becomes g m1 m2 over r squared equals mv squared over r. It's a gravitational force that's making it go around, but it's not on the surface of it, so we have to use that big equation that we don't use that often. But the nice thing about it is lots of things cancel. So when we do this, we cancel m1s, cancel one of the r's, and so we end up with, sorry, I did something. We end up with g, mass of the Earth, divided by the distance to the Earth and the Moon for the Earth, or to the satellite. I'm going to call it the distance to the Moon. And that over v squared. And so we can find that v. V then is going to be the square root of g, mass of the Earth, distance to the Moon. And we can get rid of that distance to the Moon and put instead the distance to whatever satellite we're doing if we're doing a different satellite. But that allows us to find out how fast the Moon is traveling around the Earth based on the mass of the Earth. And we have to know that, but they did some experiments pretty early to find out that. So then we can find out how fast the Moon is traveling, or any other satellite is traveling around the Earth. Pretty nice. So Kepler was a guy who looked at a whole bunch of data of the planets in the sky and realized some things. By the time he had gotten around, we knew that the planets were going basically circular around the Sun, but he did so much analysis that he figured out that it really wasn't a circle. All of them are very close to circles, but really they're ellipses. And if you remember, ellipses have two focuses from your math class. And it turns out that the Sun is always on one of the two foci. It's fun saying that word. Of the ellipse. Now, they aren't that bad. They mostly look like circles, but they're a little bit different. And it was really important at the time Kepler was coming around to be exactly right about what happened with the planets. And to do that, you had to realize they were ellipses instead of circles. One of them, which isn't a planet anymore, had a really big ellipse, and that's why Pluto would go inside Neptune at sometimes and outside sometimes, because its ellipse was a lot bigger. And that's why it wasn't really a planet like the rest of them, because they think it was captured later, not made with all of the swirling mass of mass that all the other ones were. And once you realize that you have ellipses, a lot of the motion made a little more sense. What Kepler said about the motion was that it went through an equal area for equal time. So again, it's exaggerated here. It's not quite this bad. But if it's really far away, in the same amount of time, it's going to take a tiny little wedge out of things. Whereas when it's really close, to get an equal area, it's going to take a big wedge. So basically, it's saying that it's going to go faster when it's closer to the Sun. Same thing goes for satellites that are going around the Earth. Faster when they're close. And you can quantify that, and that's what this last one he did was, he said that the ratio of their periods squared is equal to the ratio of their radiuses cubed. And that allows you to do some pretty exact measurements of how much time it's going to take for the planets to go around the Sun. Kepler. Planets. Next thing we deal with is torque. Now torque is how force is applied to make things go circularly. And so it involves not just the force that we apply, but where we apply it. So if we apply a force really close to where something is pivoting, it makes it go around more, but it makes it have less of a torque on it. Because if we apply it out of the outside, it's like a door. Like if you're trying to open a door and you push really close to the hinge, it's really hard to open it. But if you push really far away from the hinge, it's really easy to open it because you have more torque, more ability to spin something. So we have an equation, and this has a little t there, but I don't like the t. Really, torque has a little curvy top to it. So make sure and change that in your notes. You want a torque as a kind of italic T, whatever. And it's always the R perpendicular times F. And let's draw a little picture for that. Let's do a top vision of our door. And then let's say we have to define on there where it's going to pivot around. And that's called the fulcrum. It's the point it's pivoting around, and we do that by making a little triangle. That's a fulcrum. Fulcrum. Oh, hard to draw those. And that's where it's pivoting around. And then we apply a force. Let's call this up here the force perpendicular. Perpendicular meaning it's 90 degrees to the moment arm, which I'm going to call R. And R, let's do a different color because our colors are getting a little confused. R is the distance from your fulcrum to where the force is applied, R. So that R there is 90 degrees to that force, and so this is a nice easy one. We take R times F perpendicular, and that gives us the torque. So if, like for instance, this was 2 meters and I was applying 3 newtons, my torque would be 6 Newton meters. Okay, so that's a torque going around and making it go. And you can see that if my R was smaller, I'd have a smaller torque. That's why it's harder to push the door open when you try to push it right next to the thing. Right? Right. So if you ever have a force that's not perpendicular, like if you get a force going that way, all you really have to do that problem is separate it into components. You know, components are big in physics. This is the force that's parallel, and if we look for the moment arm for that, we can take this all the way back to there, and there's no distance from where this is applied to where it is. So this here, this force perpendicular is what we want. Using the angle that they would have to give us, we can take that times this whole moment arm there, and that will give us the torque if we're not at 90 degrees. Now it turns out that you can also extend this back, this force, and take the whole force times R perpendicular. That's this bit right there. We don't do that all that often. Occasionally it'll make your problem a little easier, but mainly we go with this second one, R times force perpendicular, and that gives us the sine, RF sine theta equation that we have for torque. If we go down to static torque means that it's not moving. We know what static means. And so what we'll get in a static torque problem is we'll get a bar and they'll put the fulcrum in the middle, right there. And they'll say this here is 2 meters. They'll say this there is 3 meters. Oh, I can't write on top of myself. 3 meters. I'll say over here I'm applying 5 newtons force. And I want to know what force over here would make that not move. And so basically to do static torque, we take the sum of the torques clockwise have to equal the sum of the torques counterclockwise. Since this is my pivot point, this force over here is going to make it go clockwise. And so that torque is going to be some force I don't know times the moment arm of 3. And that's going to be equal to a force I know over this side, which is going to make it go counterclockwise. That's 5 newtons times the moment arm of 2. So that ends up being a pretty easy problem. I just take 10 divided by 3. My force that I would need would be 3.33 newtons. They could give me a more complicated problem with more forces on one side, more forces on the other side, but they're not really that difficult. All I need to do is take the force times the distance over which it's applied, this force times the distance over which it's applied. I don't know what it is about circular and amusement park rides, but also this particular torque thing, the hard problems have to do with like a Ferris wheel. And you'll get 3 different cars on them. Let's say this car over here on the right is 5 newtons down, this car on the left is 2 newtons down, and then there's some car right here, and we don't know what its force is, but it's at 30 degrees, and we want it all to balance so it doesn't move. And they won't tell you what the radius is here, but since it's the same for all of them, it ends up canceling out later. And so we know that we have to do the sigma f clockwise equals sigma f counterclockwise. The clockwise one will just be 5 times, that's force times the moment arm, which is r, which I don't know. The counterclockwise ones, I'm going to get 2 times r is the easy one. Now this x1 is not at 90 degrees, so I have to get a component. You know, that's physics in 2 dimensions, that's how we do it. And so we're going to have to split it into force perpendicular and force parallel. And forces that are parallel always give me 0. And so it turns out that I'm not going to need to do this one. I just have to find the parallel one. Since this goes down to 90, this is 60, and so that interior angle there is going to be 30. So my perpendicular side is going to be x times it's the adjacent side, so it's cosine of 30 times r. So I have to get a component like that, and we're good at components. Again, I told you the r's are going to cancel. I divide everything by r. I get 3, 5 minus 2, equals x cosine 30, and so x equals 3 divided by the cosine of 30. I'm going to get a calculator quick to find that out, because, you know, it's nice to have a number. 3 divided by cosine 30, oh, that's not right. 3 divided by cosine 30 is 3.46. 3.46 newtons would be how much force I'd have to apply there to keep the whole thing from moving around. Now, sometimes this, instead of saying 5 newtons, it's actually going to tell you that it's 0.5 kilograms, and then you have to do mg, so you take 5 times 10, and so you have to do one more step in there, but I was trying to make it a little more straightforward for you, because otherwise it's not too straightforward. Last concept we're going to get to is angular momentum being constant, and that basically says that as something is spinning, there's something that remains constant with it, and that allows us to talk a little bit, not really with numbers, although occasionally they have a number, but more with concepts, how things happen when they're spinning. And it has to do with the angular momentum being I omega. Neither one of those really we talk about too much, but it ends up that I is mr squared and omega is v over r, and so what we get as constant is the mass times the radius times the velocity. And so that means that if I change the radius at which my masses are at, I can change the speed. So that's what happens with a skater. When a skater starts spinning, she puts her arms way out, or he puts his arms way out, and then he brings them in and wants to go really, really fast. And so that's how you can go really fast. Hey, there's a video, so watch. Here we go. Ready? Try again. That's me being a skater. The same thing holds true for a satellite. When something's out in orbit, if you want to catch something that's ahead of you in orbit, like this is the Earth, and this is you going around the Earth, and this is a candy bar in orbit in front of you. Now it turns out that what happens in orbit is if you change your v faster, it affects your radius. So if you just go faster, you end up spinning way away from the candy bar, and you miss your candy bar. And so to get the candy bar, what you really want to do is apply a force towards the Earth. Seems a little odd, right? But when you go towards the Earth, that changes your radius lower, which makes your velocity faster, and you catch up to the candy bar. And when you get to the candy bar, you shoot straight back out at it. And then you grab your candy bar and eat it. And that's really important for you to know, because you might end up in space and you might need your candy bar.
You gotta dodge the pots and pans.
Look at that nice vertical circle that cowboy's got going out there. That's it for circular. That's the last one. That means we're getting close to the review. We're going to have to start really getting this stuff. Ask some questions on your discussion sheet. Do it. No.